Have you ever wondered why storms rotate in the direction they do, counterclockwise in the northern hemisphere and clockwise in the southern? Has anyone ever told you that bathtubs do the same thing when they drain? Well, today we're going to talk about these things. We'll start with storms and we'll end with bathtubs. There are actually several explanations for this. I'm choosing the one that I find easiest to grasp. The first thing to realize is that we live on a sphere, and because of that, we have to use a rather complicated coordinate system to describe where things are. We use latitude, longitude, and altitude. And it's a little complicated, but we can deal with that, and by itself, that does not indicate the directions that storms should rotate. However, the crucial thing is that we live not on a sphere, but on a sphere that's spinning. And that's crucial because it means that every point on the Earth's surface is moving. It's not just moving, it's accelerating because it's changing its direction. So for example, a point here might be moving in this direction at one time, but a few hours later it will be moving in this direction. So it's changing its direction, it's accelerating. And I hope you remember that Newton's laws require a reference frame that's inertial, not accelerating. So we have to be careful in applying Newton's laws. So how are we going to do that? Well, let's start to quantify things. So, if this is the Earth spinning on its axis, and it spins in this direction, how do we represent that spin? Well, we use something called the right-hand rule. We wrap the fingers of our right hand in the direction of the spin, and the way our thumb points is called the rotation vector. Here I'm drawing it in blue, and we often label it with the Greek letter omega. So this represents this spin. And notice that this spin is not a property of just one point, it's a property of the whole body. So in particular, if we were sitting here in the mid-latitudes, we could draw the omega vector there. Now this is still pretty complicated, so let's try to develop an approximation for the rotation here in the mid-latitudes. And let's do this by zooming in on this point. So now picture the Earth as being this big. Here's the equator. And here we are sitting in the mid-latitudes. I'm going to draw the rotation vector omega very big to illustrate my point. So imagine this is omega. We can draw a right triangle and break omega down into two components. One component is here, parallel to or tangent to the Earth's surface. I'm going to call that omega parallel. The other component sticks out vertically from the Earth's surface. I'm going to call that omega perpendicular. Now let's look at each component separately. Omega parallel, if I use the right-hand rule, represents rotation like this. Now it turns out that there are other forces in those directions which dwarf the contribution by omega parallel. In particular, gravity is much larger than any contribution here. So for the purposes of our approximation, we're going to neglect omega parallel. Let's focus instead on omega perpendicular. So what does that mean? Well, again, using your right hand, if my thumb points here, the rotation is in this direction. So it's as if we have a plane tangent to the Earth's surface at our point, and the whole plane is rotating in the counterclockwise direction. In the southern hemisphere, it would be rotating in the clockwise direction. So you can think of it as looking down at your feet and seeing the Earth spin around in the counterclockwise direction if you're in the northern hemisphere. So, what does that mean? Let's think about if we're sitting at a point, again in the northern hemisphere, and therefore we are spinning in the counterclockwise direction. Let's imagine a parcel of the atmosphere here, a little parcel of air, moving along in this direction. Well, according to the parcel, we here, sitting at the mid-latitudes, are moving away in the counterclockwise direction. Turn that around. According to us, sitting here, this parcel is moving away, but it's moving away in the opposite direction. in the direction opposite to the Earth's rotation. This is an apparent force, and it's called the Coriolis force. It's apparent because it's not a real force. It's all because the coordinate system we're using is accelerating. Coriolis means that we see things in the northern hemisphere as if they are being bent to the right, and the opposite in the southern hemisphere. Now, what does this have to do with storms? Well, let's now imagine we're looking down from above, and there's a low of pressure in the region we're looking at, indicated by an L, and there are highs of pressure around it. Now, air likes to find the low of pressure. Just like water seeks the lowest point, air is seeking the lowest pressure. So the air is going to move in towards the low. And in fact, this is what makes up a storm. Because the air comes in, it has to go somewhere, so it goes up. And the air is colder higher up, so the moisture in the air condenses out, and you get precipitation over the low, a storm. So what does the air do? Well, if we're in the northern hemisphere, we know that as the air comes in towards the low, it gets bent to the right. And it keeps coming in, and it keeps getting bent to the right. And you can see that what we end up with is a swirling behavior in the counterclockwise direction. So now you know why storms rotate in the direction they do. It's because of Coriolis, which is an apparent force due to the fact that we live on a spinning sphere. Now, there are two interesting points. One is, does this happen with bathtubs? Well, let's think about it. The Earth rotates once every 24 hours. So any phenomenon you're looking at would have to last a good portion of that time, say at least an hour or two, in order to feel this effect. But bathtubs tend to drain, you hope, in less than an hour, more like minutes or even seconds. You can say the same thing from the perspective of length scales. So any phenomenon that's going to feel the effects of the Earth's rotation better be big enough, so maybe a few percentage of the circumference of the Earth, that's a few thousand kilometers. It better be that big, or it's just not going to feel the effects. Well, how big's a bathtub? Well, certainly not thousands of kilometers, and it certainly doesn't drain in hours. So a bathtub is simply too small and drains too quickly to feel the effects of the Earth's rotation. So if anyone ever tells you that bathtubs drain counterclockwise in the northern hemisphere and the opposite in the southern, just take them to your house and look at every basin you have, and you can prove to yourself they go down both ways. And the reason they go down the way they do doesn't depend on Coriolis. It depends on things like the direction the water was moving when you started it to drain, or imperfections in the surface of the basin. Now, another interesting point has to do with tornadoes. I said that phenomena have to be at least thousands of kilometers to feel the effects of the Earth's rotation. But tornadoes, which are much smaller, more like 100 kilometers across, seem to rotate in this same direction. So if you count up tornadoes in the northern hemisphere, you'll find that most of them spin counterclockwise. How could that be? They're too small to feel the effects of Coriolis. Well, you have to know something about where tornadoes come from. So here's a picture of a tornado. You can see the funnel cloud here in pink. It is spawned, it is created by a giant thunderstorm. This supercell thunderstorm is large enough to feel the effects of Coriolis. So it rotates counterclockwise in the northern hemisphere. And it gives its spin to the tornadoes that it creates. So tornadoes, even though they're too small to feel the effects of Coriolis themselves, do spin counterclockwise in the northern hemisphere because they're generated by a storm that is big enough to feel the effects of Coriolis. So thanks for listening. I hope you've learned something, and if you have, go out and tell all your friends.